In the coming decade, human beings are returning to the Moon. The Artemis Accords represent a global commitment to establishing the first multi-generational presence on the lunar surface, moving toward a continuously inhabited base. But building a permanent settlement requires a constant, unbreakable supply of electricity. Water purification, oxygen generation, and thermal control cannot safely shut down. The default solution in space is solar power. On the Moon, however, the sun sets for 14 Earth days at a time. To keep a base running through a 2-week lunar night using solar panels, you have to bring massive banks of batteries or fuel cells. The weight penalty of hauling that much storage out of Earth's gravity well makes large-scale solar power practically impossible to sustain. The other established option is nuclear. Radioisotope thermoelectric generators have powered rovers for decades, but they rely on extremely scarce plutonium-238. They operate at low efficiencies, cost tens of millions of dollars to build, and require intense political maneuvering to handle the extreme risk of launching radioactive fuel on top of a rocket. A growing lunar colony requires continuous baseload energy, similar to a nuclear reactor, but without the toxic payload or the crippling weight of battery banks. Resolving this energy bottleneck relies on a specific piece of geography, the lunar South Pole. Because the Moon has almost no axial tilt, the Sun at the poles hovers perpetually on the horizon. This creates unique topographical zones. The elevated rims of deep craters remain bathed in constant low-angle sunlight, while the crater floors plunge into eternal night. The lunar regolith has incredibly low thermal conductivity, meaning heat doesn't easily transfer through the ground. Because of this, a peak of eternal light on the crater rim bakes at 400 degrees Kelvin, while just a few kilometers down, the permanently shadowed crater floor sits at 100 degrees Kelvin. Curious, this creates a massive, stationary 300-degree temperature gap maintained naturally for billions of years. In thermodynamics, anytime you have a constant hot source adjacent to a constant cold sink, you can build a heat engine. This is a schematic of the proposed Lunar Thermosiphon System. It's a closed-loop pipe network that bridges these two extreme temperature zones to extract usable electricity. First, working fluid flows through a serpentine array of titanium pipes laid flat on the sunlit regolith. As it absorbs the 400 Kelvin heat, it boils, turning from a liquid into a highly pressurized vapor. That high-pressure vapor races toward the crater's edge and forces its way through a turbine generator. The physical expansion of the vapor spins the radial blades, converting thermal energy directly into an electrical current. Exhausted of its pressure, the low-energy vapor drops vertically down the shaded crater wall. Here, exposed to the 3 Kelvin vacuum of deep space, the pipes rapidly radiate their heat away. The vapor cools and condenses back into a dense liquid. Evaporation, expansion, and condensation. This fluid cycle constantly chases thermal equilibrium, turning the rim of the crater into a fuel-free power plant. In a zero-gravity environment like the International Space Station, circulating fluid requires heavy, power-hungry mechanical pumps. Here, we have to get the liquid back up the cliff to start the cycle over. The Moon provides 1/6 of Earth's gravity. By routing the condenser pipes vertically down the crater wall for at least 137 meters, the weight of the falling liquid column generates significant hydrostatic head pressure. The falling fluid physically pushes itself back up the return pipe, circulating entirely on its own weight. But dropping fluid into a 100 Kelvin shadow introduces a severe risk. If the working fluid gets too cold, it will freeze solid and burst the pipes. This graph illustrates the operational window of the working fluid. Pure water would freeze instantly, and pure ammonia would generate internal pressures too high for lightweight aerospace tubing to handle. By utilizing a specific zerotropic mixture of 30% ammonia and 70% water, the system takes advantage of the Kalina Cycle. The ammonia acts as a potent antifreeze, pushing the freezing point down to -55 degrees Celsius while keeping maximum pressure at a manageable 35 bar. The combination of the crater's vertical drop and the ammonia chemistry cleverly eliminates the two most common failure points in space-bound power systems. To survive indefinitely, the hardware itself has to be exceptionally rugged. Conventional turbine bearings require oil lubrication, but in a vacuum, oil immediately outgasses and boils away. Instead, this system utilizes magnetic levitation, or gas foil bearings, using the ammonia vapor itself to keep the spinning turbine suspended without physical friction. Then there is the threat of micrometeoroids. With no atmosphere to burn up incoming debris, a single puncture could cause a catastrophic vacuum boil-off. Surrounding the pressurized titanium core is a vacuum gap and an outer layer of Kevlar and Nextel fabric. This Whipple shielding shatters the impactor into a harmless cloud of dust before it ever reaches the high-pressure fluid. A single 10-kilowatt unit provides enough continuous baseload energy for a small habitat. Because the design requires no nuclear fuel, these thermosiphons are entirely modular. You can endlessly daisy-chain them. Eventually, hundreds of these loops could tile the exact circumference of Shackleton crater's rim. This sprawling power web would harness the natural thermal gradient of the pole to supply megawatts of uninterrupted electricity, enough to run heavy lunar industry and large-scale water extraction. Survival on the moon requires us to treat its most hostile features, the absolute dark and the baking sun, as raw materials for engineering. The crater engine converts the moon's own topography into a self-sustaining power grid.